Alright, so today's notes. Last time we talked about logistics curve, right? What the logistics curve looks like, what all of its parts mean. Today we're going to look at applications of it. Alright, so the first application we're looking at is population growth for otters. Alright, so we've got a river of otters, or a river otter population in areas being studied. The population is modeled by a logistics curve, and most populations are. Usually they start out growing fairly fast, then they start to slow down, and then eventually they taper off due to space, resources, and other things. There's just so much. There's only a limit to how many people, or in this case otters, can live in this particular region. All right, so again, it's a specific area. So our otter population is modeled by this P of T function, where P of T is the otter population T years after the study began. All right, so the first question is just asking what's the initial value? How many otters were there at the start of the study? So that would be at time 0. And so you plug 0 into the logistics equation. Alright, and I'm going to round to the whole otter if I need to. It comes out 150, remember units, so 150 otters at the start of the study. Alright, so 150, that says otters, if you can read that. Alright, we're going to do a lot of this graphically, and so we're going to base it on the graph. So I'm going to graph the function, and then we'll talk about, explain and justify your answer. So again, based on the graph of the function, what appears to be happening after many, many years. And so I'm going to graph this in the calculator. Alright, so I'm going to graph the P of T. Alright, so I'm going to change my window before I get started, because a standard window won't work. Now I'll probably leave my minimums negative 10 in both the x and the y direction, just because I can see my axes then. What I am going to change is the maximum. So my x maximum is going to change and my y maximum is going to change. And I'm going to kind of look at the problem and see if there are any numbers that the problem gave me, and it doesn't really give me any numbers. So I'll probably do my x maximum. I'll probably go maybe 30. We'll start with 30. My y maximum has to do with the top number, right? I remember that's that horizontal horizontal asymptote. There we go. Horizontal asymptote. And so that's what my population is going to approach as time goes on. And so I need to make sure I can see that. And so what I'm going to do is I'm going to go a little bit past that. I'll probably go to 3,500 just so I can see that point. And so I'm going to type it in the calculator. So again, hopefully you have your calculators with you and you can follow along and type it out and change your window so that you know what you're doing. I am going to eventually maybe have a video on the calculator as soon as I need one more sort of thing to come in from the mail. And if I do, then I can at least show you what's going on. Alright, so if you've graphed that out, you've set your window, and so first quadrant is the only place where we're going to graph it, right? Because population is positive, time is positive, so this is years. Right, that's the T. This is P of T, which is otters. Starts off at 150, so I'm just going to mark off kind of low here, 150. And then I'm going to do a dotted line for my asymptote. Remember, that's the y equals 3,000, right? Has to do with that carrying capacity number, this number here, right? The top number. And then that's what it's approaching. So it's starting here and then approaching. Oops, doesn't cross it though. Just approaches it. Alright, approaches that number. So your calculator should have this shape out on it. And so explain what, and there's different ways you can explain it. You can explain it as a limit, or you can just say, as time goes to infinity, right, as my t values go to infinity, the maximum population for the otters is estimated to be 3,000 otters. Alright, the rate at which they're growing will eventually slow down too. Alright, so that's what the population will reaching, and in terms of the derivative, right, the rate of growth for the population. You can read this. I might erase this and start with the rate of growth. Alright, so I can fit it in here. Same thing, as time goes to infinity, the rate of growth. So, as time is going off to infinity, the rate of change, which would be the rate of growth, of the otter population is approaching 0. Right? Its rate of change, its slopes are getting closer and closer to 0. Right? There's no more growth. It's reached its maximum. This particular region can't have any more otters. Alright? So again, it's reached its maximum population. Its rate of growth is slowing down. Alright, the second part here. Alright, when will the population of river otters reach 1/2 its carrying capacity, and what is significant about that fact? Alright, you can solve this graphically or by hand. It's just up to you. So if you're solving it graphically, alright, so there's the graph that's on your calculator. What you're going to do is you're going to graph when it reached 1/2 carrying capacity. So at 1/2 the 3,000, so that would be 1,500. And so you're going to graph a second line. You're going to y equals 2 is 1,500. Leave the population function in there. Alright, and so it'll graph this horizontal line which represents 1,500. This is the point we're looking for, right? That is my inflection. Right, that's what's important about it. It's the inflection point. Alright, and so that's the moment we're looking for. We want to know when that happens, the time that it happens, right? The time that it reaches that 1,500, that half the carrying capacity. And you do this on your calculator by, once you've got the graphs, you've got the original graph, you've got the horizontal line at 1,500, and then you're going to find it by using the intersect key, which again, we talked about this earlier in the semester. Just to remind you where it is, you have to hit second, trace on your calculator. It's the 5th one down. It says intersect. And then it'll ask you first curve, second curve, and guess. And just get as close as you can to that moment. And hit first curve, second curve, and guess. And then it should give you out the time, alright, which would be the x value. And it comes out to 5.89. Alright, so in 5.89 or about 6 years, if I round to 6 years. So again, in 5.89 or about 6 years, they reach 1/2 the carrying capacity. Alright, that's solving it, and we'll talk about why that's important, but that's the first part of the question, alright? When will, and then we'll talk about what's significant in a little bit. Alright, that's if you solve it graphically. That's perfectly fine to do that. The alternative to graphically would be solving it by hand, which means you're going to take your 1,500, set it equal to your population equation. So you'd set your 1,500 equal to the 3,000, 1 plus 19e to the 0.5t, and solve that. And again, we practiced solving these when we reviewed exponential. So the first thing, again, I would do is multiply both sides by the denominator. So that gets multiplied over here. So you get 1,500 equals times the 1 plus 19e to the negative 0.05 equals 3,000. Divide by that 1,500. Forgot my t there. Subtract 1, so you get 19e to the negative 0.05t equals 1. Divide by 19. And so I got the e term isolated finally. So the e term equals 1 over 19. Leave exactly 1 over 19 because my next step is to take the natural log. Alright, the natural log cancels those out, leaves me with my negative 0.05t equals the natural log of 1 over 19. Last step, divide by that negative 0.05. Was it 0.5 or 0.5? I wrote 0.5 in all of these and it should have been 0.5. wrote it right at the first part of them. All right, it should be 0.5. So again, where it really matters is to make sure you get it right here. This is what I'm going to plug in. My natural log of 1 over 19 divided by 0.5, which should give you this t value. Should come out 5.89, which is about 6 years. All right, so it's up to you, by hand or graphically. All right, so now we're going to talk about why is that significant? Why is that inflection point significant? All right, and I'm going to look at the graph to sort of talk about it. All right, so I'm going to write it here. So give me a second while I erase this. All right, so remember, at half the carrying capacity, all right, so in about 6 years, that's the inflection point, all right? Inflection is at t about 6 years, all right, where it reaches. So first of all, one important aspect is that we are at half the maximum the population can be. All right, and then the second thing about it has to do with the rate of growth. So remember, in this first piece up to the inflection point, it's concave up, right? And so before the inflection point, the population was growing. So for the first 6 years, the otter population was increasing at faster rates. It's the fastest at the inflection point. So at that 6th year, or at the 5.89, so at the inflection point is when it's growing the fastest. All right, it has the biggest slope, biggest rate of growth. After that, the population's growth slows down. All right, and approaches 0. The rate of growth approaches 0, slows down until the rate of growth is 0. All right, we'll eventually flatten out. So that's, again, there's a lot of important stuff going on. So I'm going to go look at the graph and how to talk about it in terms of the graph. So good luck reading that. Hopefully you caught what I said. All right, so again, this first piece growing faster and faster, right? So it's growing, so it's concave up. It's growing faster. At the inflection point, it's its fastest rate, biggest slope. And then after that, it's going to slow down, right? That's the concave down shape. So now we're still increasing, but we're increasing at slower rates until eventually, once we get out here, it approaches a 0 growth rate slope. Right? And again, that's how logistics cover. Eventually, the population's going to max out, and it's not going to get any bigger, right? It's going to stay at the maximum. All right, the next example. All right, this is an example of actually what I talk a little bit about, kind of what we're going through right now, right? Just an FYI on this. All right, so a lot of viruses, actually almost all viruses, especially seasonal ones like the flu, tend to follow a logistics curve. And so that's what this next example is. And even the coronavirus that, kind of shutting the world down right now, it's going to follow a logistics curve. All right, we're at the sort of beginning of the logistics curve, and we're kind of hoping to flatten it out. I guess what they're talking about when they talk about flatten it out, so that beginning part still going to grow, but grow slower rate. But eventually it will start to taper off. All right, and again, probably a lot of times things tend to taper off over the summer because viruses aren't as viable in the summer. That's what happens with the flu. All right, so this is a flu example. Suppose that Again, we're going to look at the flu season. So flu epidemic. So suppose the flu is going through Fort MacArthur, all right? And so it's a population. We, again, will follow the logistics curve. There's an estimated so many people who will get the flu. And eventually, though, it will max out. Everybody who's going to get it will get it. All right, so this is the logistics curve that we're going to look at that is going to model the flu epidemic at Fort MacArthur. All right, so T represents the days after the start of the flu, all right, kind of the flu season. Usually flu season somewhere around December to January. All right, so I'm going to graph it. All right, so when we go to graph it, all right, so I'm going to solve most of this graphically. So I'm going to graph this function. Now I will have to change my window a little bit. I'm going to change my x max and my y max. Again, I'm going to leave my minimums the same as before. I'm going to kind of look and see what I need. So, and I'm going to plug 15 and 40 in. Alright, so I know I need to at least go beyond 40. So I'll probably go to make sure I can see what's going on. I'll probably go to at least 60. Alright. Then my y maximum again has to do with the total we expect, which is the top number here, the 5,000. So I need to make sure I go to at least 5,000. So I'll probably go 5,500. Alright, when I go to graph that. So that's what I'm going to change my window to. Alright, so this would be time in days. This would be number of soldiers with the flu. Alright, I'm just going to kind of mark off its starting point, so that would be the number at the start of the flu season. And then I'm going to mark off my asymptote. Remember, the asymptote's that 5,000, which would be the maximum we expect to get the flu during the flu season. Alright, so again, this is the way most viruses work, especially, again, like I said, the flu and seasonal viruses. Alright, you're going to have initially it's going to grow pretty fast, right? Concave up. This is sort of where we are at the coronavirus. And so this is growing really fast, right? This would be the exponential growth part. There will eventually become a place when half of the people we expect to get it. And after that point, it does start to slow down, all right? And eventually it will taper off to there's barely any new cases and it'll approach a rate of growth of 0. And that's, again, what we're hoping to do by flattening it out is we're hoping to make this first part, it's going to grow, but we're hoping we're going to make it grow slower, right? Instead of really fast, which again is what it's wanting to do. By quarantining people, we're going to hopefully make this grow slower so people who get it at a slower rate. So it's a slower S-curve, a more elongated S-curve than something like this. Alright, so this would be the F of T, the number of people who get the flu at the fort. Alright, now the first question, how many soldiers will we expect to contract the flu by day 15? So I'm going to plug 15 into my formula, plug 40 into my formula. Or you can use the graph. Since you have the graph, you can always hit second trace value and plug in the value 15 and the value 40. Now remember, these are people, right? Soldiers. So just round to the whole person. We don't want a fraction of a person. It doesn't make sense to have, 0.7 of a person have the flu. So just round accordingly. So the first one comes out 507.75, so I'm going to round to 508. Alright, so again, 508 people are soldiers, have the flu by day 15. Alright, now 40 days later. Alright, so we're going to plug 40 in again around to the whole person. So that comes out 4,988.4, so I'm just going to round 4,988. So a lot more, right? There's, again, 500 day 15. That's where it's the exponential growth, so it's growing pretty fast. Alright, soldiers have or had. This could also mean 40 days in it. These people all got the flu. Some of them might already be better now, right? Not all at once, right? 4,988 people had the flu. Some of them have it, and some of them had it, and they could be better at this point. Right? This is just how many have got the flu at the fort. Alright, soldiers have the flu. And I put an E on flu. By day 40. Alright, how many soldiers are expected to eventually get the flu? Again, what's the maximum number we expect? All right, so they expect 5,000, right? That's that carrying capacity, right? 5,000 soldiers at the fort to eventually get the flu. All right, and so that's the maximum. After five, again, their expectation again is around 5,000. After that, it should taper off and no new cases of the flu should happen. All right, after again about that much of the population gets it, no new cases should occur. It should be at this edge where it's starting to flatten out over here, right? No new cases, it's starting to zero out. Now, some people got the flu out of the 5,000, right? Some of them got it early, some of them got it here in the middle, and some of it got it here at the end. Remember, this would be the total of over X amount of days. We expect to have 5,000 people at most get the flu. All right, so that would be the expectation. Once that happens, all right, the epidemic is over. All right, and hopefully some of those people have already gotten better. All right, what's the inflection point? What does it tell you about the application? All right, so the inflection point is when it's half capacity. All right, so we're looking for the inflection point is when 1/2 the total that we expect to get it. So half is at 2,500 have gotten the flu. That's when our inflection point is, and we want to know when that happens. So we want to find how many days are we at half the number of soldiers who are going to get the flu. All right, so again, there's two ways to do it. The last example I showed you both ways. This example, I'm just going to solve it graphically. All right, so I'm going to graph y2. I'm going to graph that 2,500. And so I'm going to go up to my picture here. And so 2,500 is halfway. Graph that line. That's the line y equals 2,500. This is the inflection point. All right, which I'm going to find it using my second trace. Select 5, the intersect. First curve, second curve, and guess. And that'll tell me when the inflection point occurs, and then we'll talk about why that's important. All right, so again, you type it in, you pick second trace 5, intersect, first curve, second curve, guess. All right, comes out to 21.6 is when it happens. So 21 days, 21.6 days into the flu epidemic, we reach our inflection point. All right, so 21.6 days is when 2,500 people, our soldiers, will have got the flu. Again, some of those people are new cases, but some of them are old cases and they've gotten better. And this is sort of the point we want to reach with the coronavirus. We want to slow it down so we don't reach it right away, otherwise too many people will be getting the coronavirus right away and overwhelm the health system. But we expect so many people to eventually get it. It's just we're hoping to spread that out. As soon as we reach whatever they think the halfway point is, it'll slow down. All right, so as soon as half the people they expect to get the virus get it, then we're in the, all right, it's slowing down, will eventually taper off phase. And that's sort of where we want to get to, but we want to get there slower. We don't want to get here really fast. We want to get here, again, 21 days is pretty fast to reach that maximum. We want to slow that down and maybe reach it in 50 days or something like that. So that's just sort of putting it in terms of today. All right, so again, why is the inflection point important? Well, this is when it's going to sort of slow down. So in 21.6 days, after 21.6 days, the flu epidemic at the fort will slow down. Fewer and fewer people will be getting the flu at slower and slower rates. So slow down and approach 0. a rate of 0, right? Which is the goal. No new cases, right? No new cases. Everyone who have had the flu would have already caught it, and then some of those will have gotten better. Some of those will be new cases, but the new cases will be fewer, right? And so that's why it's sort of important to reach that halfway point. Once we reach this halfway point, again, people are getting the flu, but fewer and fewer of them, right? Half the population's already got it. It's starting to slow down, and again, more people are getting the flu here, but a bunch of people have already got it, right? And they've gotten better because they were in this first push, and they've gotten better. All right, and so again, until we sort of taper off until no new cases, all right, and that's sort of the goal we want to get to, and so get past that halfway point. All right, how fast is the flu spreading T days after the epidemic starts? So this is asking you for your derivative. So I'm going to write my equation down. All right, so again, there's my equation. And so we just want the derivative, right? The rate of growth. All right, I am going to have to use my quotient rule. All right, my low function's that expression. My high function, this is just a constant. All right, so it would be the low times the derivative of the high, but the derivative of the high is just 0, right? 5,000 is a constant. And so when I take its derivative, it zeroes away. Then it's minus the high, so minus the 5,000 times the derivative of the low. And so I'm just looking at my low function. The 1's a constant, it'll zero out, so really it's just the derivative of the e term. So remember, the derivative of the e term is itself, so I write down that number. But then I'm not done yet, right? That's the derivative of the outside. Then I have to remember times the derivative of the inside. So it's times that negative 0.33. All over the low function, that entire thing, so put parentheses around it, squared. So make sure you have this set of parentheses. It's important because that's that whole term squared. All right, so it's up to you. I will probably clean this up. I can take this number times this number times this number. All right, so I'm going to rewrite it with the top as simplified as I can get it, which again just means multiplying those out. So it's negative 412.7 e to the negative 33 times time. All right, so there is my rate of change function. All right, that's how fast the flu is spreading at T days after the start of the epidemic, right? The slope, all right, the rate of change, which is my derivative. All right, then we ask you to use it. How fast? So what's the speed? The epidemic was spreading in 15 days. So you just take your 15 and plug it into that derivative equation. You could check your answer graphically, and my rule of thumb would be to do that. Again, I'm going to round to the whole person. All right, so it comes out 150.5 when I plug that in. And so I'm going to run into 151. And then don't leave the answer 151, right? Put it in context. All right, the speed, right, would be a change in my function over the change in time, right? Like speed is easiest thing to think about is miles per hour. So this would be soldiers who get the flu per day, right? So after 15 days, the flu was spreading at a rate, speed, of 151 new cases, 151 soldiers with the flu, or get the flu, per day, right? It's per day. All right, so 15 days into the epidemic, that's how fast the flu was spreading. All right, that's its rate of spread. That's not how many people had it, right? How many people had it? If we go back to the first problem, right? 508 people have it in 15 days. This is how fast it's increasing. This is how fast it's growing in 15 days, which would be one of its higher rates, because 15 days is pretty close to its inflection point, which is the fastest speed, right? The inflection point was at 21, so 15, if I go back to my picture, right, 15 would be around right here, and so this would be when it's growing fairly fast, right? So it's spreading kind of fast here. Remember, this is when it's spreading the fastest, and then we slow down. Alright, so that finishes up the problem. It kind of puts things in perspective too with what's kind of going on today. So we're going to wrap it up there. That finishes up the 3.3 notes. Alright, so we'll start into the 3.4, which is decay models. Alright, and that's where we'll start the next set of notes.